All right, so we'll finish up section 4.2 today. This is the last section that we do any graphing by hand. Any other graphing we do tomorrow will be on the calculator. So this is what we did yesterday. We looked at problems where the degree of the numerator was either smaller than the denominator or equal. Today, we're going to switch that. Now we're going to look at graphing rational functions where the degree in the top is larger than the degree in the bottom. Okay. So as I said earlier, once the degree in the top is larger, then that means horizontal asymptotes go away. Yay, horizontal asymptotes. But that means we have another kind of asymptote. The simplest asymptote you can have that's not horizontal is probably a slanted one. And then from there, they get worse. They're curved. So now you have a dotted, curved asymptote, which that's a little harder to deal with. Okay, but we're definitely going to look at the slant. Any questions on what we're going to do? Yeah.
You said it was a graphing actual function where the top of the fraction is larger than the bottom?
Yeah. So it'll be problems like this. The degree in the top is going to be larger than the bottom, where yesterday it was more like that. The degree in the bottom was always larger. All right. So when the degree in the top is larger, there's this new thing that we can find, and it's called the end behavior asymptote. It's a little different than the end behavior model, and I think on the next page, or at some point, I talk about the difference between the end behavior asymptote and the end behavior model. So we'll get to that. All right, so let's suppose that you have a rational function. Okay. H of x is the numerator, g of x is the denominator. What would that actually look like in a problem? Something like that. In this case, the numerator is 2x cubed minus 4x squared and all that stuff, and the bottom is x minus 2. So you got a polynomial on the top, polynomial on the bottom. When you divide them, using long division or synthetic division or whatever kind of division you use, you get a quotient and you get a remainder. I'm calling the quotient q of x and the remainder r of x. Remember, when you divide polynomials, sometimes your remainder is not a number. Sometimes it is, depends. Sometimes it's a letter, sometimes it's a number. Okay, so remember how we can write our answer. Okay, let me, for a second, just pretend f, h, and g are all numbers. Okay, so let's go back to like a third grade kind of problem. Let's say we had, let's do 13 divided by 4. All right, if I do that out, what's my quotient? Yep. 3. And what's my remainder? 1. So I can take that answer that I have here with q colon r colon. You can write it that way. Or you could write it this way. Quotient plus remainder over divisor. So let's write it that way. Quotient. Quotient was 3 plus my remainder, 1 over my original denominator, my divisor. It was 4. So if you wanted to know what's 13 divided by 4, it's 3 plus 1/4. Or as a mixed number, you would say 3 and 1/4. We're going to do the exact same thing. When we do the division, we can write our answer just like that, even if it's polynomials. It's the same idea. But the only thing that's important is what's right there. Okay? What I've circled, the quotient. Okay? We don't care about the remainder. We don't care In fact, we don't care about it so much, it's gone. Right? We don't care about that part at all. Okay? The quotient is the end behavior asymptote. So you already know how to find the quotient. It's doing something we did last week. It's just doing out long division. It's just now I'm not calling it the quotient anymore. I'm going to call it the end behavior asymptote. Okay. So to find an end behavior asymptote, do the division, and whatever you get for the quotient, that's the answer. So we're going to look at one right now and see if we can figure out the end behavior asymptote. All right. So find the quotient, the remainder, and the end behavior asymptote of this problem. Right. Now, you can tell how bad of an end behavior asymptote it's going to be by looking at the degree in the top, looking at the degree in the bottom, and comparing those two numbers. What's the degree in the top? The highest? 3, yep. And what's the degree in the bottom? Not the term, just the degree number. Yeah, 1. So it's on the x, and the degree is right here. It's a 1. The difference between 3 and 1 is a 2. That means this asymptote is a degree 2. Okay, degree 2s are curved asymptotes. They look like parabolas. They are parabolas. So let's find out what it is. So we're going to put x minus 2 on the outside. 2x cubed minus 4x squared. Don't forget 0x plus 3. Now, because it's x minus a number, I could have used synthetic division. That's faster. But I'm going to do long division because long division works all the time. Synthetic only works if it's x minus a number. All right. So let's start 2x cubed divided by x. How about Isabel? What's 2x cubed divided by x? Close. Something in front of it as well. 2x squared. So we get 2x squared. Multiply it back out. 2x squared times x. And then 2x squared times negative 2 is negative 4x squared. And what do we do with those columns when we do long division? Subtract. Actually, it's going to be kind of nice right here. 2x cubed minus 2x cubed is gone. What's negative 4x squared minus negative 4x squared? That cancels too. That doesn't always happen, but this time it did. And now you're basically done because, I mean, you can keep going, but if you bring down your next terms, and I say, okay, x goes into 0x, how many times? Well, 0. And then if I multiply 0 back out, I just get 0x, and 0 times negative 2 is 0. So really, I mean, this isn't really doing anything. 0 minus 0 is 0. 3 minus 0, we just have the 3 we were left with up above originally. So the remainder is 3. Do we care about the remainder? No, all I care about is the quotient. So let's write down what they want to know. Quotient. Okay. What's my quotient here? 2x squared. All right. Well, in terms of, I said, do we care about the remainder? They asked for it. Is it really important to do anything else? No. But they did ask for it, so I'll write it. What was the remainder? 3. It's useless to do anything else with. And now the EVA. What's the end behavior asymptote? 2x squared. It's the same as the quotient. So it's like we kind of asked for the same thing twice. If they asked for both of them, yes, the quotient and the EVA are the same thing. Because that's how you get the EVA, find the quotient. Yeah. Okay. Any questions on that? Okay. So, a couple important points, but, especially the difference between the EBM and the EBA. The EBA is when you do long division. The EBM is when you just take the highest degree term in the top and divide by the highest degree term in the bottom. So the process to calculate them is different. Any question on the difference between how you find the EBM and the EBA? EBM was yesterday. EBA is what I just showed you right now. Sometimes, even though it's a different process to find them, sometimes they come out the same, sometimes they come out different. If I look back at the problem we just did, the highest degree term in the top is 2x cubed. The highest degree term in the bottom is x. What do I get if I do 2x cubed divided by x?
2x squared.
I get 2x squared. And if you're thinking, well, why didn't we just do that then if it comes out the same? Well, sometimes it comes out the same. The only reason the EBM and the EBA are the same here, well, a couple things. One, you had this canceling out right here. Not only did the first term cancel, the second one canceled with it. That's part of the reason the EBM and the EBA are the same. The second reason they're the same here, you didn't have an x term. So we had to fill in a 0. That's the other reason why they came out the same. If those hadn't canceled and that wasn't a 0, this long division would not have come out the same as the EBM. Okay. But in this case, it did. Okay. And the third point, I think I already mentioned it, but now I'm writing it. If the degree of the numerator is less than the degree of the denominator, all your asymptotes are straight. Horizontals and verticals. If the degree of the numerator is larger, like we just did in the last problem, degree 3 was in the top, degree 1 was in the bottom. When that happens, asymptotes can be curved. Now, I'm going to show you the graph of a curved asymptote. I'm not going to spend a lot of time on it, but I'll show it to you on the calculator. I want to spend more time on the slant asymptote. Okay, this is the only case that they can be curved, when the degree in the top is larger than what's in the bottom. So any questions on that? When you can get a curved asymptote and when you can't. Okay, so let's take a look. And this is more just a calculator question. We're going to graph the original problem we just did long division with. We're going to graph 2x squared, which we think is the EVA, and we're going to show that it is, okay, graphically. Okay, we already showed that it is algebraically. Let's do it graphically. Okay, so I need to go back and I need to look at the original problem because I don't remember what we had. So we had 2x cubed. Let's get rid of that. And put this in parentheses. 2x cubed minus 4x squared plus 3 divided by x minus 2. And I'm going to graph the EVA in red right below it. We think it's is it 2x squared? And what I'm going to do is I'm going to make it a thinner line. Because I want you to be able to kind of see, if it's too thick, they overlap quickly because there's not a lot of resolution on the screen. So I'm going to make the line thinner by highlighting the color, hitting enter, and then I don't care if it's red, you can leave it as red. But I'm going to go down, and I'm going to press the left arrow one time. And that just change it from a thick to a thin line. And then press OK. Now my Y2 will be a little thin. If you don't change it, the thickness it's not a huge deal. Right, let's do zoom 6. Okay, I might have to zoom out a little bit because I don't think you're going to see the whole graph. Okay, what you're looking at there is kind of like half the graph. All right, so let's make this bigger. Let's take this, put that here. Okay, that red line is, or that red curve is supposed to be an asymptote. Does everyone see how the graph in blue is getting closer and closer and closer to the red? It's like the space between them is getting smaller. That's because we have a curved asymptote. That's what it would look like. Now, we should have more of a parabola. What's happening is, though, it's off the screen. So if I set my Ymax at like, let's try 40. Okay, there's the part we had before. And there's the other part. And let's wait for the graph in red. Let's look at it again. Now you can see on both the left and the right side, the graph in blue and the graph in red getting closer and closer and closer. That space in there is getting smaller. So it's basically like a parabola. Right? Your parabola is right here. It wants to connect. Okay? It tries to connect. But the reason it can't is because, look at the denominator. What number could you plug in for x to make the bottom 0? 2. So what that means is there's a vertical asymptote at 2. So if I just put that in, it'll be a little clearer to see. And you know what? I'm going to make that a little thinner too. So let's move the whole graph. Okay, so there's your vertical asymptote. So the graph in blue is coming down. It's trying to connect. It wants to follow that curve in red, but it can't. That green dotted line, it's like a brick wall. Okay, it starts coming towards it. It's like, wait a minute. Oh, I got to stay close to it, but I can't cross it. So what do? I just curve, and I just keep going down. Okay. Same thing here. Think of the parabola coming in from the top. Okay, it's coming in. It wants to stay on that wants to stay on that red curve, but then all of a sudden, it's getting close to that green dotted line. It can't. So as it comes down, it's trapped by that green dotted line, and it has to curve back up again. Okay? And that's what it looks like. So the more you zoom out, the more of the parabola you would see. But any question on that idea? So that's what a curved asymptote can look like. Okay. Right, so let's try sketching this one by hand. What's the degree in the top here? 3. So that's a degree 3 polynomial. That's the highest exponent. What's the degree in the bottom? 2. What's the difference between a 3 and a 2? 1. It's a difference of 1. So this asymptote is not going to be quite as complicated as the one we just looked at. Right? It's a degree 1. Degree 1 is a line, but it's not a horizontal. It's going to be a slanted line. So let's find everything they want. So let's start with vertical asymptotes. You can start with whatever you want. Bless you. Okay, so just like we always do, we got to factor the bottom to make the zeros easy to find. These problems are already complicated enough. I'm not going to give you something that doesn't factor, because then you're going to use quadratic formula. Okay, so let's try to factor it. Can anyone tell me how the factoring would finish up from there? Yeah?
It would be x plus 3 and
Minus 1. Let's try it. We get x squared. That's good. Minus x plus 3x. Minus x plus 3x is 2x. Yep. Okay. So I'm going to have two vertical asymptotes. Isaac, where's my first vertical asymptote going to be? Yep. So we're going to have one at -3. We're going to have another one at +1. Let's put those on the graph. -3, +1. Now, because there's two vertical asymptotes, this is actually the hardest one we're going to sketch by hand today. So we're starting out with that one, and then the next one we do, it's actually going to be even easier than this. So if you understand this one, you're good. So -3, +1. All right, we've got those. What else do they want? End behavior asymptote. Okay, so off to the side, I'll do that. I need to do out the long division. So x squared plus 2x minus 3. Well, I think I can squeeze it in here. X squared plus 2x minus 3 divided into 2x cubed plus 7x squared. Don't forget the 0x minus 4. Okay, so let's start by dividing x squared into 2x cubed. Nick, if I divide x squared into 2x cubed, what do I get?
You would need 2x.
Yep, I agree. 2x. Multiply it back out to everything. 2x times x squared is 2x cubed. How about 2x times 2x? 4x squared. And 2x times -3. -6x. And subtract. 2x cubed minus 2x cubed is gone. 7x squared minus 4x squared, 3x squared. Now the rest doesn't really matter. Okay, I can finish this row off, but it doesn't matter. 0 minus -6 is +6. Now normally you'd also bring down the -4. That's not going to matter either. The only thing that matters is to divide this by that, and you're done. If you wanted the remainder, you'd have to keep going. But I don't care about the remainder. So what's 3x squared divided by x squared? 3. There's my end behavior asymptote. 2x plus 3. Not as bad as a parabola. It's a line with a slope of 2 and a y-intercept of 3. So just write that down. That takes the place of a horizontal. There's never a horizontal asymptote when the degree in the top is bigger. We still have the verticals. Now I'm going to sketch 2x plus 3. Yeah?
So the EVA is always the quotient?
The EVA is always the quotient. Yep. So put a dot at 3, and then remember, slope is rise over run. Up 2, right 1. So up 2, right 1. 1. Do it as many times as you want, and then put in a dotted line. Let's go like this. Yeah, it's pretty good. Okay, so what I basically have, if you ignore the axes, is I just created 6 sections, kind of like we did yesterday. 1, 2, 3, 4, 5, 6. There's your 6 sections. We never draw in all 6. Where do we draw? I'm going to use the calculator to help me figure that out. Usually we end up drawing in like 3 of the sections. Okay, it's never more than 3 of them. Right. So I'm going to check values very close to those numbers. Okay, so if I haven't typed it in, I need to type it in. So 2x cubed plus 7x squared minus 4 divided by, that all needs to change, x squared plus 2x minus 3. Okay, what's a value that's really close to negative 3, but just a little smaller? Yeah.
Negative 3.01.
Sure, negative 3.01. I'm way down. You can ignore y2, that was the previous problem. So let's do it like that. So just to the left of negative 3, we're way up. Okay, way up at positive 121. Okay, so way up there. Let's check a value bigger than negative 3. Negative 2.99. When I type in negative 2.99, I'm at negative 1200. That's way down. Right? So let's make this a little smaller. So way down here. All right. Let's try the next one. What's a value just a little smaller than 1? Sure, it's 0.99. So I'm at negative 120. Way down there. And a value just a little bigger than 1. I'm up at over 1,000. So way, way up. So when we sketch this, the graph is not allowed to cross any asymptotes. So I can already tell you where the sketch is going to be. It's going to be in that section, that section, and that section. It has to be, because it can't cross any of those dotted lines. It doesn't look like those squiggles. So let's, I'm still not 100% sure what it looks like. So I'm going to check some more x values in the left section. Let's try negative 1, negative 2, negative 3. Let's try negative 4. All right, negative 4, negative 4. 1, 2, 3, 4. 1, 2, 3, 4. For me, that's enough. I can tell what this is going to look like. If you want to do more points, you can. But the idea is you've got to stay extremely close here. You've got to stay extremely close in here. And those two have to connect. So it's just going to come down and do something like this. Just staying really close to the dotted line the whole time. Okay, so that's that part. Let's check the middle. Okay. So let's check some other x values. Let's try like negative 1 and see where we're at. Negative 1, I'm down at 1/4. So again, very, very close to that dotted line. So that graph in the middle section in the bottom is going to stay very close to 3 dotted lines. The 2 verticals and the slant. Let's do 0. 0, I'm at 1.3. So I'm up here. All right, I think that's enough for me. If you need more, you can. But you've got to stay very close here. You've got to stay very close here. And it's got to, those 2 lines I just drew have to connect and go up through the 2 dots. So it's got to do something like that. That's how that section has to look. Now, the problem with this other section, where this dot is, it's already off my graph. It's up. It's going to be up pretty high. So let's try like 1.5 and see if we can get that on the graph. Just barely. My graph only goes to 10. So 1.5, I'm at 8.2. So 3, 4, 5, 6, 7, 8. I'm right here. So I'm trapped in a V section, and I have to stay very close to each side of the V. So what it's going to look like is like this. It's going to come down, and it's going to look like a V. Okay, let's hit graph and see how we did. Let me do zoom 6, because that's what my window is. So you're just barely seeing a little curve up in here. That's that part in the upper right. Then you've got this part, looks kind of flat in there. Mine looks a little flatter than it should be. Maybe it should be a little more curved, but that's fine. And then this part that comes down and curves. All right. So it just takes a little practice using the table and trying values. Okay. That's the harder one, because it's got 2 vertical asymptotes. But that EBA, that's called a slant asymptote. Wow, that's good. That's called a slant asymptote because it's on a slant. Right. So as far as the test tomorrow, I wouldn't worry too much about the first kind of asymptote we did that was curved. I would focus more on the slant asymptote. There will be a problem. I'm sorry, the test is curved. Yeah, test is curved. No. Sorry, it's not hard test. This is not tomorrow. Okay. So any questions on that? It's a little weird, but it's, you just use your table and just keep typing in numbers. You can do 15, 20 points if you need them. But remember, you're never going to cross the dotted lines. So you're trapped in those sections. And the lines or curves have to hug those dotted lines. They've got to stay right up next to them the whole time. Okay. All right, let's try this one. Actually, you know what? I want to do another slant, but I want one that's easier than that one. So let's call that example 7, right? Let's call this 7B. By the way, my numbering continues from the examples from yesterday. That's where that's from. Let's try x squared minus 3x minus 7 divided by x plus 3. Graph. So implied in the word graph is find the asymptotes and all that stuff. Okay, let's start with the vertical. What's the vertical asymptote here? Yeah, it's just -3. That's going to be a little easier this time. So now we only have 1 to deal with instead of 2. There is no horizontal asymptote. Degree in the top is bigger. How much bigger is the degree in the top than the degree in the bottom? 1. It's 1 bigger. Degree in the bottom is 1. Degree in the top is 2. That's a difference of 1. Difference of 1 equals slant asymptote. So let's find out what it is. X plus 3 into x squared minus 3x minus 7. Okay, so Alec, if I divide x into x squared, what do I get?
Just x.
Just x. Multiply it out. X squared plus 3x and subtract. That first part is always 0. Megan, what's negative 3x minus positive 3x?
Minus 6x.
Minus 6x, good. Be careful you don't say, oh, they cancel. No, not quite. It's minus 6x. Now you can bring down the 7, but the 7 doesn't matter unless you're going for the remainder. What's negative 6x divided by x? Yep, negative 6. There's your end behavior asymptote. It's a line with a slope of 1, y-intercept of 6. Okay, so now we're ready to sketch. I'll draw my 2 asymptotes, and then I'll check other points as needed. Okay. So let's put a graph. Let's make that a bit bigger. The vertical was at -3. Okay. Put that there. And the slant is x minus 6. So y-intercept is -6. I think I got enough room, it'll still fit on the graph, hopefully. And the slope was what? 1. So up 1, right 1. Okay. If you put enough dots, you really don't even need to draw the asymptote, because the dotted, it almost looks like a dotted line because I put so many anyway, but I'll put it in. Yeah, Sam?
Wait, how'd you get the -6x minus 7? Kind of missed that part.
The x, so that's when you do x, -3x minus 3x is -6.
Oh, so that's
And then -7, I just brought it down.
okay. Is that the remainder?
We didn't finish it to find the remainder because all we cared about was the quotient.
Okay.
If I wanted the remainder, I'd have to multiply the -6 back out to both and then subtract. And then that would be the remainder.
Okay.
But I didn't find it because I don't need it. Okay, so let's check some values. The only lousy part is going to be is if the graph ends up in here, it's going to go off my grid. So we'll see what happens. What's a good value to check for x here? Negative what? Yeah, I'd say -2.99. I need to type it in first. So x squared minus 3x minus 7 divided by x plus 3. All right, so if I check -2.99, -9. Okay, I get positive 1,000. So at -2.9, it's way up. So I don't think it's going to end up in this section. No, yeah, it might. So what's another value I can check besides -2.99? Yeah, -3.001. I'm at -11,000. So down here. All right, and let's get one more point, and I think that'll be good enough. Let's do -1, 2, 3. Let's do -4 and see where that ends up. All right, so in terms of graphing, this one, it goes off the graph, but we know from everything else we've done, you're trapped in this section. Okay, you can't go outside that section, and you've got to stay very close to each dotted line. So it has to look something like that. It's the only way it can look in that section. Okay. Same thing in this other section. Although here I'm on the graph a lot more, so if I want to get some other points, I probably could. If I try 0, -2.3, so that's a good one. Let's do 2. I get -1.8. All right, so I'm starting to get an idea of the curve. I think that's enough. So it's going to come down. It's going to start curving to go through those points. And then it's going to get closer and closer. So it's got to stay near the dotted lines, except for where it does that turn. You know, because it's got to turn to start heading towards the other one. But that's pretty much what your sketch looks like. So if I wanted to see this on the graph, I got to set my y-min way lower than -10, probably like -30. Yep. So there's the two sections. Again, I'm zoomed out a little differently than my graph here, but that's fine. Okay. Any questions on that one? So most people like that one a little better because there's less asymptotes, so you don't have to test as many sections. There's only 2 sections you're drawing in. All right, so the last thing I want to look at, and this is purely on the calculator. I'm not going to do anything by hand. I just want to graph that. Okay? I just want to see what happens. It's going to just remind you to do something. So let's type it in. 2x to the fourth. Let's see. And if you look at the highest degree term in the top, look at the highest degree term in the bottom, you should have an idea of what kind of asymptote is going to be in this problem. Does anyone have a guess? It's a degree 1, which is, yeah, a slant. Yeah, it's going to be a slant. Because the degrees are off by 1. Right? And divided by x cubed minus x plus 50. Okay, I'm going to start with zoom 6. All right, so we've typed it in. Let's start with zoom 6. Okay, so there's my graph. I can kind of start to see a slant. I bet what's going to happen here is it's going to curve back. Let me, instead of the standard window, let's try going up to 30 and see if we can see the slant a little better. Yeah, there we go. So if I were to put a line in here, it would be getting closer and closer to that line. So I definitely can see a slant. This bottom section, I don't think anything particularly wonderful is going on. It's just, that's just what the bottom section looks like. So in terms of a big picture, I think this window is fine. It's a good window. So those are the values I used. But is there anything in that graph that looks like we might want to check it out a little closer? Well, this part, I think from here, this is just going to continue that way. That's just going to go like that. That's just going to go like that.
It doesn't look like a straight line on that side.
On that side? No, it does curve a little bit. I think it'll start to look straighter, though. I think the curve you're seeing right in here, that's it. It's not going to curve again. But anything else on there that I might want to check out a little closer? Something there looks kind of suspicious. I'm skeptical of something.
It goes almost completely flat across the zero.
Yeah. If I look between, what is that, -1, -2, between -4 and 2, it looks almost completely flat. Let's zoom in right there and check that out. So let's try, what is that? -4 to 2. So -4 to 2. And let's set our y min -1 to 1. So let's really zoom in on that. Let's go -1 to 1. And I think we're starting to see something, but I'm not sure that that's enough. So here's a zoomed in picture of that. What does it look like is happening there? It's, what do you mean by overlapping?
Like we're in between like the one and the two, I guess. It looks like there was something that was like getting started and then they just like stopped almost.
Like right in here?
Yeah.
Yeah, something weird's happening. So let's zoom in. Let's zoom in to just this. Let's go like -0.1 to 0.1. So now we're really zoomed in. -0.1 to 0.1. Let's see what we're looking at. So, if we zoom in there, I think that's enough. We can tell that it wasn't flat at all. Big picture, if you zoom way out, that's a good window to see the big picture. That's what you need to see everything that's happening. But if you want to see the detail, we can actually see it's crossing the axis 1, 2, 3, 4 times, which there's no way I could tell that from the big picture. It just looked pretty flat. So the point of that is just make sure you, if something looks like it's real flat, or if it doesn't, if you can't tell very clearly what's happening, zoom in and check it out. Any questions on that? That's all I wanted you to see. Okay, so the homework tonight, I think somebody wanted me to add to it though. No. So it's page 235, it's 40, 41, 45 to 47, and 51 to 55.